Last time we watched a network teach itself a curve that nobody ever wrote down. It got there by being wrong, over and over, and flinching in the right direction every time. One hidden layer, 8 units, 99.5% on these 200 dots. But there is a word I have leaned on in both of these videos and never once explained. Squash. Every unit multiplied, added, and then squashed. I told you what it does. It keeps the running total inside a fixed range. What I never told you is why that is there at all, and it turns out to matter more than almost anything else in the network. So today we take the squash out of the middle and find out what it was actually doing there. Because here is the intuition nearly everybody has, and it is wrong. A network is powerful because it is deep. Layers stack. Each one builds on the last. More layers, more power. Let us test that directly, and let us be scrupulous about it. Same 200 dots, same network, same starting weights, identical to 4 decimal places. 2 inputs, 8 units, then another 8 units, then one answer. 105 numbers in total. One change, and only one. In the middle, instead of squashing its total, each unit now passes that total straight through, untouched. Multiply, add, and then nothing. That is the entire modification. Watch what it learns. It is training. That is a real run. The loss really is falling, and it really is getting better. And there it is at 2,000 steps. 88%. Which is not a terrible score. But never mind the score. Look at the shape of it. It is a straight line. 105 numbers. 2 full hidden layers. 16 units in the middle. And what it drew is the same thing one single neuron drew in episode 1. So the obvious move is more layers. That is the intuition, so let us actually spin them, and let us give depth every advantage. Every one of these was trained at 7 different step sizes and keeps its best result. 1 hidden layer, 33 numbers, 88%. 2 hidden layers, 105 numbers, 88%. 4 hidden layers, 249 numbers, 88%. 8 hidden layers, 537 numbers, 88%. And now look at the loss underneath each one. 0.2744, 0.2744, 0.2744, 0.2745. Not close to each other. Identical to 3 decimal places, and the last one is off by a single 10,000th. 537 numbers bought precisely nothing over 33, and every boundary is a straight line. So this is not a training failure. Something is structurally wrong here, and it comes down to one line of algebra. Take the first layer. 2 numbers arrive, and it multiplies them by a 2 by 8 block of weights. 8 numbers come out. The second layer multiplies those 8 by an 8 by 8 block. And the last layer multiplies those by an 8 by 1 block and adds a bias. 3 multiplications, one after another, with nothing at all in between them. And multiplication has a property you learned when you were about 7 years old. Multiplying by 3, and then by 4, is multiplying by 12. You never needed the 2 steps. There was always a single number that did the same job. Matrices behave exactly the same way. Multiply these 3 blocks together, and you get 1 block. A 2 by 1, 2 weights, and 1 bias left over. So I did it. I took this trained network, multiplied its 3 weight blocks together, and folded every one of its biases into one number. 2.6644 minus 7.2827 minus 0.0309. 3 numbers, which is exactly, precisely, what episode 1 was about. And here is the test that matters. I ran all 200 dots through the full 105 parameter network and through that one little neuron and compared what they said. The largest disagreement across all 200 dots was 3.3 times 10 to the minus 16. That is not close. That is floating point rounding error. Those two things are not similar. They are the same function. Which means the depth was never real. That 8-layer, 537-number network is a 2-weight neuron wearing a very convincing costume. And that explains the 88% exactly. In episode 1, I searched every straight line that exists on a dataset rather than sampling a few. Let me do the same thing here. Every angle, all the way around. And at each angle, every position that line could possibly sit at. The best straight line that exists for these 200 dots gets 89.5%. Our deep network got 88. So it did not merely fail to beat a straight line. It could not quite reach the best one. And you could stack 1,000 of those layers, and that ceiling would not move by 1/100%. It is not a limit on how well it trains. It is a limit on what the thing is. So let us look at what the squash was doing, and let us look in the exact place where it happens. This is a horizontal cut, straight through the middle of the data. For every position along that cut, I have plotted what each of the last layer's 8 units contributes to the final answer. With no squash, here they are, 8 straight ramps. Some tilt up, some tilt down, some steeply, some barely at all, but every one of them is straight. Now add them together, which is precisely what the final layer does. The total runs from -2.56 on the left to +2.5 on the right, and it does it in a straight line. I measured how far that total bends away from a perfectly straight line, anywhere along the cut, 1/10,000th. And that is the whole problem in one picture. You can add straight ramps together all day long, in any combination, with any weights. You will always get another straight ramp. Now put the squash back. Same cut, same network shape, same starting numbers. The only difference is that each unit's output gets bent before it is passed along. And look at the pieces now. They are not ramps anymore. They rise, and then they flatten off. Now add those together. It bends. It climbs, comes back down, and climbs again. Distance from a straight line, 12.87. That is what a nonlinearity buys you, and it is genuinely the only thing it buys you. It makes the pieces bendable, so that their sum is allowed to have a shape. So put it back into the network, and run the identical experiment again. Same 200 dots. Same 105 numbers, same starting weights, same 2,000 steps, same step size. The only difference between this run and the one you watched at the start of the video is one function in the middle. It begins the same way. 25 steps in, it is at 89.5%, which is exactly the ceiling we just measured for a straight line. And then it does the thing the linear version was not merely bad at, but mathematically incapable of. 100%. Loss, 0.0018. 88 to 100, out of the same 105 numbers, in the same 2,000 steps. Nothing was added. Nothing was made bigger. One function in the middle simply stopped being a straight line. Which raises a question I did not expect to find interesting. How much bend do you actually need? So I built a dial. At 0, each unit passes its total straight through. At 1, it is the full curve. In between, it is a mixture of the two. And I trained a fresh network at 10 settings of that dial, each one at its own best step size, so that nothing here could fail merely because it was badly tuned. At 0, 88%. That is the straight line we have been looking at all video. 0.5% of bend, 88. 1%, 88. 2%, 88. 5%, still 88. Which is worth being precise about. Any bend at all makes the function technically nonlinear, but a network that is technically nonlinear and practically straight learns like a straight one. 10%, 89. 20%, 92.5. 35%, 99. 60%, 100. So it is not a switch that flips. It is a ramp, and it comes on somewhere around 1/5 of the way. And the smooth curve is not sacred either. Here is the crudest bend anyone has ever bothered to propose. Below 0, output 0. Above 0, pass it straight through. One kink, and it is not even smooth there. That is a ReLU, and it is what very nearly every modern network actually uses. Same network, same starting weights. 100%, the same as the smooth curve. And you can see what it is built out of. That boundary is not really curved at all. It is flat panels, hinged together. Enough hinges and flat panels will approximate anything you like. That is honestly the whole idea. So here is what a layer actually is, once and for all. Multiply by a matrix. Bend. Multiply by a matrix. Bend. Take the bends out, and that entire stack is one matrix, and no amount of depth will change it. This is not small print. Remove the activation functions from a transformer with 175 billion parameters in it, and the whole thing collapses to a single matrix multiply. Every layer, every attention block, all of it, one linear map, and you could write it on a page. The depth in deep learning is not bought by stacking layers. It is bought by refusing to let them merge. Which finally brings us to the word all three of these videos have leaned on without ever defining: loss. I have been putting a number on screen, calling it loss, and telling you that smaller is better, as though that were obvious. It is not obvious, and it is not one number. Next time, what wrong actually means, how choosing that number differently changes what the network learns, and why the most obvious choice is usually the wrong one. A stack of straight lines is just a straight line,